Greetings everyone and welcome to the final video lesson for Chapter 5 of the Foundations of Scalable Systems. And in this lesson we're going to delve into how we horizontally scale our services. A core principle of scaling a system is being able to easily add new processing capacity to handle increased workload. For most systems, a simple and effective approach is deploying multiple instances of stateless server resources and using a load balancer to distribute the requests across these instances. This is known as horizontal scaling and is demonstrated here on the slide. Stateless service replicas and a load balancer are both necessary for horizontal scaling to be effective. Service replicas are deployed on their own virtual hardware. If we have 2 replicas, we potentially double our processing capacity. If we have 10 replicas, we potentially have 10 times capacity. This enables our system to handle increased loads. The aim of horizontal scaling is to create a system processing capacity that is the sum of the total resources available. The servers need to be stateless so that any request can be sent to any service replica to handle. This decision is made by the load balancer, which can use various policies to distribute requests. If a load balancer can keep each service replica equally busy, then we can effectively use the processing capacity provided by the service replicas. Horizontal scaling also increases availability. With one service instance, if it fails, the service is unavailable. This is known as a single point of failure and is generally a very bad thing, something to avoid in any scalable distributed system. Multiple replicas increase availability. If one replica fails, requests can be directed to any replica. The system will have reduced capacity until the failed server is replaced, but it will still be available. The ability to scale is crucial, but if a system is unavailable, then even the most scalable system ever built is somewhat ineffective. So load balancing aims to effectively utilize the capacity of a collection of services to optimize the response time for each request. This is achieved by distributing requests across available services to ideally utilize the collective service capacity. The objective is to avoid overloading some services while underutilizing others. Clients send requests to the IP address of the load balancer, which redirects the request to the target service and relays the results back to the client. This means the clients never contact the target services directly, which is also beneficial for security, as the services can live behind a security perimeter and not be exposed to the internet. Load balancers may act at the network level or the application level. These are often called Layer 4 and Layer 7 load balancers respectively. The name refers to their network transport layer at Layer 4 in the OSI stack, the reference model, and the application level at Layer 7. The OSI model defines network functions in 7 abstract layers, as you can see here on the slide. Each layer defines standards for how data is packaged and transported. Network load balancers distribute requests at the network connection level, operating on individual TCP or UDP packets. Routing decisions are made on the basis of client IP addresses. Once a target service is chosen, the load balancer uses a technique called network address translation, NAT. This changes the destination IP address in the client request packet from that of the load balancer to that of the chosen target. When a response is received from the target, the load balancer changes the source address recorded in the packet header from the target IP's address to its own. Network load balancers are relatively simple as they operate on the individual packet layer. This means they are extremely fast as they provide few services beyond choosing a target service and performing network address translation. In contrast, application-level load balancers reassemble the complete HTTP request and base their routing decisions on the values of HTTP headers and the actual contents of the message. For example, a load balancer can be configured to send all POST requests to a subset of available services, or distribute requests based on a query string in the URI. Application load balancers are sophisticated reverse proxies. The richer capabilities they offer means they are slightly slower than network load balancers, but the powerful features they offer can be utilized to more than make up for the overheads incurred. This slide compares the 2 load balancer types in a simple application scenario. The load balancing technology under test is the AWS application and network elastic load balancers. Client load varies from a lightly loaded 32 concurrent clients to a moderate load of 256 concurrent clients. Each client sends a series of requests with no delays between receiving the results and sending the next request. This exerts the highest load possible from the number of requests on the services. You can see that the network load balancer delivers on average around 20% higher performance for the lower loads, up to 128 clients. This validates the expected higher performance from the less sophisticated network load balancer. For 256 clients, the performance of the two load balancers basically converges. This is because the capacity of the service replicas that they are distributing requests to is exceeded by the system, and the system has formed a bottleneck. At this stage, the load balancer's throughput is basically the same. In general, a load balancer has 4 different types of features as shown on the slides here. It has a series of loaded distribution policies, it does health monitoring, it will do elasticity, and it will handle session affinity. Let's look at what these mean on the next slides. Load balancer distribution policies dictate how the load balancer chooses a target service to process a request. Any load balancer worth its salt will offer several load balancing distribution policies. For example, HA Proxy, a leading open source load balancer, offers 10. Those listed on the slide here are 4 of the most commonly supported across all load balancers. Load balancers will also allow services to be allocated weights. For example, a standard service instance in the load balancing pool may have 4 virtual CPUs and each is allocated a weight of 1. If a service replica running on 8 virtual CPUs is added, it can be assigned a weight of 2 so that the load balancer will send twice as many requests its way. A load balancer will periodically send pings and attempt connections to test the health of each service replica in the load balancing pool. These tests are called health checks. If a service becomes unresponsive or fails connection attempts, it will be removed from the load balancing pool and no requests will be sent to that host. If the connection to the service has experienced a transient failure, the load balancer will reincorporate the service once it becomes available and healthy. If, however, the service has failed, the service will be permanently removed from the load balancer target pool. Spikes in request loads can cause the service capacity available to the load balancers to become saturated, leading to longer response times and eventually request and connection failures. Elasticity is a capability of an application to dynamically provision new services to handle an increase in load. As the load increases, new replicas are started and the load balancer directs requests to these new instances. As load decreases, the load balancer stops services that are no longer needed. Elasticity requires a load balancer to be tightly integrated with application monitoring so that scaling policies can be defined to determine when to scale up and down. Policies may specify, for example, that the capacity for a service should be increased when the average service CPU utilization across all instances is maybe over 70%, and capacity should be reduced when the average CPU utilization decreases below 40%. An example of elastic load balancing is the AWS autoscaling groups. An autoscaling group is a collection of service instances available to a load balancer that is defined with a minimum and maximum size. The load balancer will ensure that the group always has the minimum number of services available and the group will never exceed the maximum services available. Elasticity is a key feature that allows services to scale dynamically as demand grows. For highly scalable systems with fluctuating workloads, it's pretty much a mandatory capability for providing the necessary capacity at minimum costs. Session affinity or sticky sessions are a load balancer feature for stateful services. With sticky sessions, the load balancer sends all requests from the same client to the same service instance. This enables the service to maintain in-memory state about each specific client session. There are various ways to implement sticky sessions. For example, HA Proxy provides a comprehensive set of capabilities to maintain client requests on the same service in the face of service additions, removals, and failures. AWS Elastic Load Balancing generates a HTTP cookie that identifies the service replica a client session is associated with. The cookie is returned to the client, which must send it in subsequent requests to ensure session affinity is maintained by the load balancer. Sticky sessions can be problematic for highly scalable systems. They can lead to load imbalance, in which over time clients are not evenly distributed across services. This is illustrated on the slide here, where two clients are connected to one service, one to another, and none are connected to this service here. Load imbalance occurs because client sessions last for varying amounts of time. Even if sessions are evenly distributed initially, some will terminate quickly while others will persist. In a lightly loaded system, this tends to not be an issue. However, in a system with millions of sessions being created and destroyed constantly, load imbalance is pretty much inevitable. This will lead to some service replicas being underutilized, while others are overwhelmed and may potentially fail due to resource exhaustion. To help alleviate load imbalance, load balancers usually provide policies such as sending new sessions to instances with the least connections or the fastest response time. These help direct new sessions away from heavily loaded services. Stateful services have other downsides. When a service inevitably fails, how do the clients connected to that server recover the state that was being managed in memory? If a service instance becomes slow due to high load, how do clients respond? In general, stateful servers create problems that in large-scale systems can be difficult to design around and to manage. Stateless services have none of these downsides. If one fails, clients get an exception and retry, with their request routed to another live service replica. If a service is slow due to a transient network outage, the load balancer takes it out of the service group until it passes health checks or fails. All application state is either externalized or provided by the client in each request, so service failures can be handled easily by the load balancer. Stateless services enhance scalability, simplify failure scenarios, and ease the burden of service management. For scalable applications, these advantages far outweigh the disadvantages, and hence their adoption in most major large-scale internet sites such as Netflix. So that's it for the video lessons for Chapter 5, in which we've examined how we design APIs for services, how we deploy them, and how we horizontally scale them. In our next set of lessons for Chapter 6, we're going to start examining the issue of caching. Thanks for watching.